Somewhere in the universe, right now, there is a place where space itself ends, where the laws of physics as we understand them simply stop applying, and where time, as you experience it tonight, means something entirely different. Welcome to the Sleepy Lab. Tonight, you will drift through one of the most quietly astonishing structures in all of nature, a black hole. We will begin at the very beginning, with how one forms and what that invisible boundary surrounding it actually is. And we will let the science carry you gently, unhurriedly, towards sleep. If these slow journeys through the universe bring you peace, consider subscribing, one sleepy soul at a time. Now, let's begin. Close your eyes a little more. Somewhere out there, a star has reached the end of a very long life. For millions, sometimes billions of years, it burned, hydrogen fusing into helium, helium into carbon, carbon into heavier and heavier elements. That burning was a kind of balance. The outward pressure of all that nuclear fire held the star's own gravity at bay. But eventually, the fuel runs out. When it does, gravity wins. The core of the star collapses inward with extraordinary speed. In some cases, the collapse is so complete, so total, that all that mass is compressed into a region almost unimaginably small. And when that happens, when the density crosses a certain threshold, something remarkable occurs. The escape velocity exceeds the speed of light. Escape velocity is simply the speed something would need to travel to break free from a gravitational pull. From Earth's surface, that speed is about 11 kilometers per second. Fast, but achievable. But compress enough mass into a small enough space, and the escape velocity climbs. It climbs past the speed of any rocket, past the speed of any particle we know, and eventually, it climbs past the speed of light itself. And light is the fastest thing there is. So once that threshold is crossed, nothing escapes. Not matter, not energy, not light, not information of any kind. A black hole has formed. Now, there is a boundary around this region, a threshold, a point of no return. It is called the event horizon. The name is quietly poetic. An horizon, in the ordinary sense, is simply the limit of what you can see from where you stand. The event horizon of a black hole is something similar. It is the limit beyond which no event, no occurrence, no signal can ever reach you. Whatever happens past that line stays there, forever. But here is something worth sitting with for a moment. The event horizon is not a wall. It is not a surface you could touch or feel. There is no membrane there, no barrier with any physical substance. It is a geometric boundary, a feature of the shape of space-time itself. The curvature of space and time in that region becomes so extreme that all paths, every possible direction, anything could travel, curve inward toward the center. It is less like a wall and more like a drain. Once you are past it, every direction you can move, forward, backward, sideways, every direction leads deeper in. There's no outward anymore. The geometry simply does not permit it. The mathematics that describes all of this came together in a remarkable way. In 1916, a German physicist named Karl Schwarzschild was serving on the Eastern Front during the First World War. In the middle of that, surrounded by the noise and hardship of a battlefield, he found time to read a paper Albert Einstein had just published, The General Theory of Relativity. And within weeks, Schwarzschild had derived the first exact solution to Einstein's field equations. A solution that described, mathematically, the space-time around a perfectly spherical mass. He sent his calculations to Einstein from the front. Einstein presented them to the Prussian Academy of Sciences on Schwarzschild's behalf. Schwarzschild died a few months later from an illness contracted at the front. He never saw what his equations would eventually come to mean. What he left behind was a precise description of curved space-time around a collapsed object, and embedded in that description was a specific distance, a radius, that would later carry his name. The Schwarzschild radius? It is the radius at which the event horizon forms for a non-rotating black hole, and it scales directly with mass. The more mass you compress, the larger the event horizon. The relationship is clean and proportional. But the numbers, when you sit with them, are quietly extraordinary. Take the Earth. Our planet has a mass of roughly 6 times 10 to the power of 24 kilograms. If you were to compress all of that mass, every ocean, every mountain, every layer of rock and iron all the way to the core, into a sphere small enough to form a black hole, that sphere would need to be roughly 9 millimeters across. About the size of a marble. All of Earth in a marble. And at that point, the escape velocity from its surface would equal the speed of light, and an event horizon would form around it. The Earth itself would not change. Its gravity, felt from a safe distance, would be exactly the same as it is now. The Moon would continue its orbit undisturbed. It is only the compression that matters, only the density. Now consider the Sun. The Sun is roughly 300,000 times more massive than the Earth. Its Schwarzschild radius is about 3 kilometers, 3 kilometers across. For a star that currently spans nearly 1.5 million kilometers in diameter, the Sun would need to be compressed to the size of a small city before its event horizon could form. These numbers are not meant to alarm. They are simply the quiet arithmetic of gravity, the universe doing what it does, following rules laid down long before any of us arrive to observe them. And yet, somewhere out there, these compressions have happened. Stars far more massive than our Sun have collapsed, and the event horizons have formed. And the Schwarzschild radii have become real, physical boundaries in the fabric of space. Not theoretical, not hypothetical, real. The universe contains these places, quietly, in the dark between galaxies, at the centers of galaxies, scattered through the arms of galaxies like ours, patient, invisible, and governed entirely by the same equations a man worked out in a trench more than 100 years ago. Let that settle over you now. The mathematics of a battlefield letter, describing the geometry of the most extreme objects in the cosmos. There is something very still about that. Stellar mass black holes, the kind born from collapsing stars, typically contain somewhere between 3 and several tens of times the mass of our Sun. 3 solar masses? 10? 30? Those numbers feel manageable, almost modest when you say them quietly like this. But hold them against what exists at the centers of galaxies. At the hearts of large galaxies, including our own, there are black holes of a different order entirely. Not stellar remnants, not the collapsed cores of individual stars, but structures containing millions, sometimes billions, of solar masses, compressed into regions that, vast as they are, would still fit within the boundaries of our solar system. Let that scale settle for a moment. 1 billion suns, each one a star that could swallow the Earth 1,000,000 times over. And all of that mass, all of that gravity, gathered into a single region of curved space-time, smaller than the distance from the Sun to its outermost planets. The universe does not do things by halves. At the center of our own galaxy, roughly 26,000 light-years from where you are lying now, there is one of these objects. It is called Sagittarius A, a name that sounds almost gentle for something of its nature. It contains the mass of roughly 4 million suns. 4 million? Not 4 million stars scattered across a galaxy. 4 million solar masses concentrated at a single point in the geometry of space, a point around which the entire inner structure of the Milky Way quietly organizes itself. Stars orbited. Some of those stars complete full orbits in just a few years, moving at thousands of kilometers per second, tracing tight ellipses around something they will never touch and never escape if they stray too close. We have watched them, tracked their paths over decades, and from those paths, we have measured the mass at the center with quiet precision. 4 million suns. Invisible, but not unknown. For most of human history, black holes were mathematical objects, solutions to equations, things that the universe permitted but that no one had ever seen. And then, in 2019, something changed. A collaboration of radio telescopes spread across the Earth, from Hawaii to Chile to the South Pole, linked together to form an instrument roughly the size of the planet itself, and turned their attention toward a galaxy called M87, about 55 million light-years away. What they were looking for was a shadow. Not the shadow of a solid object, but the absence of light in a region where gravity had bent every nearby photon either inward or into tight curves around the event horizon, a dark circle surrounded by the glow of heated gas and lensed starlight. And they found it. The image that emerged from months of processing and calibration was not sharp by ordinary standards. It was a blurred ring of orange and gold, warm and uneven, with a darker region at its center. But that dark region was real. It was the shadow of a black hole. The first time in history that a human instrument had resolved the immediate vicinity of an event horizon. The black hole at the center of M87 contains roughly 6.5 billion solar masses. 6.5 billion. The number is almost too large to hold, but the image makes it concrete in a way that numbers alone cannot. There it is, a circle of darkness, surrounded by light that has been bent and compressed and brightened by the most extreme gravitational field we have ever directly observed. The bright ring around the shadow is not simply the glow of nearby gas, though that contributes. It is also light that has traveled paths no straight line could describe, photons that have looped partway around the black hole before escaping outward toward us, photons from behind the black hole, bent around it by the curvature of space-time, and redirected toward our telescopes across 55 million light-years of space. That ring is gravity made visible. It is what space-time curvature looks like when you can finally see it. There is something very quiet about that image. If you have ever looked at it, it does not announce itself. It does not roar. It simply sits there, a circle of warmth around a circle of nothing, and asks you to understand what you are looking at. You are looking at the edge of the knowable. Beyond that dark boundary, the laws of physics, as we currently understand them, continue to apply for a while, but they lead somewhere we cannot see, and perhaps somewhere they themselves cannot fully describe. But we are not there yet. For now, we are still outside, still in the realm of what general relativity predicts with confidence, still in the region where the mathematics holds and the observations confirm it. And there is much more to understand here, in this outer region, before we consider what lies within. The black hole at the center of our own galaxy, Sagittarius A Sagok, is quieter than M87's, less actively fed, less surrounded by the bright turbulence of infalling gas. It sits at the center of the Milky Way, in a kind of relative stillness, its presence known almost entirely through the motions of the stars around it. We have never imaged it with quite the same clarity as M87, Though in 2022, the same collaboration of telescopes produced an image of Sagittarius A**us as well. A harder task, because the gas around it moves and shifts on timescales of minutes rather than days, blurring the signal even as the telescopes gather it. But the image came. Another shadow, another ring, another confirmation that these objects are not abstractions. They are there. Both of them, the 155 million light years away and the 126,000 light years away, both described by the same equations, both obeying the same geometry, both surrounded by the same kind of bent and redirected light. The universe is consistent in this way. It applies its rules everywhere, at every scale, across every distance. The Schwarzschild radius that describes a black hole of 4 million solar masses is simply 4 million times larger than the one that would describe a black hole of 1 solar mass. The geometry scales, the physics holds. And somewhere between the stellar mass black holes scattered through the arms of galaxies and the supermassive ones anchoring their centers, there may be intermediate mass black holes as well. Objects of thousands or tens of thousands of solar masses, harder to find, less well understood, but suggested by certain observations in certain dense star clusters. The universe may have filled in the range between small and enormous. It tends to fill in ranges. But for now, let the two ends of the scale rest in your mind. The stellar remnant, a few times the mass of the sun, born in the collapse of a single star, and the supermassive anchor, billions of solar masses, whose origin is still not fully understood, still debated quietly among the people who spend their lives thinking about these things. How does something become 6.5 billion solar masses? The honest answer is that we are not entirely certain. Growth through accretion over billions of years, mergers of smaller black holes, seeds formed in the early universe under conditions that no longer exist, perhaps some combination of all of these. The universe keeps some of its methods to itself, and that is all right. There is something restful in the idea that the cosmos holds questions we have not yet answered, that the dark at the center of every large galaxy contains a mystery we are still, slowly, learning to read. You do not need to solve it tonight. Neither do we. And so we turn gently from the question of how black holes grow to the question of what they do to the space around them. Because a black hole does not simply sit there, inert, in the dark. It reshapes everything nearby. Not violently, not with noise, but with a quiet, total authority over the geometry of space and time. And one of the most visible signs of that authority is what happens to light. Light, which travels in straight lines through empty space, does not travel in straight lines near a black hole. It cannot. Because near a black hole, space itself is curved, and light, faithful to the geometry it moves through, follows that curve. So when light from a distant star passes close to a black hole on its way toward us, it bends. Not scattered, not absorbed, simply redirected, as though the black hole had reached out and gently turned it. The result is that we see the star in the wrong place. Or rather, we see it in several places at once. The same star, the same source of light, arriving at our eyes along multiple curved paths, each one bent by a slightly different angle, each one tracing a different arc around the black hole. What we observe, then, is not a single point of light, but a distorted arc, sometimes two arcs, sometimes a smear of brightness stretched across the sky. This is gravitational lensing. And it is not a trick of perception, not an illusion in any dismissive sense. It is the universe showing us, directly, that mass curves the path of light. Einstein predicted this, and the first confirmation came in 1919, during a solar eclipse, when astronomers measured the positions of stars near the edge of the sun and found them shifted just as the theory said they would be. Near a black hole, the effect is far more extreme than near a star. The curvature is deeper, the bending more severe. And under the right conditions, something remarkable can happen. If a distant source of light, a black hole, and an observer all fall into perfect alignment, a single straight line through space, then light from that source can travel around the black hole in every direction simultaneously and still arrive at the observer. Not as a point, not as an arc, but as a complete ring. A circle of light surrounding the dark silhouette of the black hole. This is called an Einstein ring. And it is, in its quiet way, one of the more beautiful consequences of general relativity. A halo formed not by any physical structure, but by geometry alone. By the simple fact that mass tells light which way to go. These alignments are rare. The universe does not often arrange itself so precisely. But they have been observed, and each one is a small confirmation that the mathematics describing curved spacetime is not merely an abstraction. It is a description of something real. Now, as we move closer to the black hole in our minds, the bending of light becomes more extreme. And there is a place, a specific region just outside the event horizon, where the curvature becomes so severe that light no longer bends around the black hole and continues on its way. It bends all the way around. It orbits. This region is called the photon sphere. For a non-rotating black hole, it sits at exactly 1.5 times the Schwarzschild radius, halfway, in a sense, between the event horizon and the space beyond. Within the photon sphere, a photon moving in exactly the right direction at exactly the right angle can travel in a perfect circle, looping endlessly around the black hole, never escaping, never falling in. If you could somehow stand there, which you could not, for reasons we will come to, but if you could, you might, in principle, see the back of your own head, light from your face, traveling forward, curving around the black hole, returning from behind. The geometry of that place is unlike anything in ordinary experience. But the photon sphere is not a stable home for light. The orbits there are what physicists call unstable. A photon circling in the photon sphere is balanced on a kind of knife's edge. Any small disturbance, any tiny deviation from the perfect circular path, and the photon does not simply wobble and return to its orbit. It commits inward, toward the event horizon, falling into the black hole and never returning. Or outward, escaping into space, carrying with it some faint image of whatever it passed near. This instability is why the photon sphere is not filled with light trapped forever in endless loops. Photons pass through it. Some are captured, some escape. And the ones that escape carry information about the region to distant observers. They are part of what creates the bright ring visible in images of black holes, the glow that surrounds the dark shadow at the center. That shadow, incidentally, is larger than the event horizon itself, roughly 2.5 times larger as far as we can measure. Because the shadow is not the edge of the event horizon, it is the edge of the photon capture region, the boundary within which any photon aimed at the black hole will inevitably spiral inward. The event horizon hides behind it, a little smaller, a little deeper in the dark. And now, a step further inward. Beyond the photon sphere, closer still to the event horizon, we reach a boundary that matters for matter rather than light. For anything with mass, any particle, any fragment of gas, any object with substance, there is a closest orbit that can be maintained without inevitably falling in. This is called the innermost stable circular orbit. For a non-rotating black hole, it sits at 3 times the Schwarzschild radius, twice as far from the center as the photon sphere. Outside this boundary, matter can orbit the black hole indefinitely, just as planets orbit a star, pulled inward by gravity, kept in motion by their own momentum, tracing stable ellipses or circles through space. Inside this boundary, that balance cannot be maintained. Not because the physics changes abruptly, not because there is a wall or a surface, but because the geometry of space-time in that region no longer permits a stable circular path. Any matter that crosses inward of the innermost stable circular orbit will spiral inward. Not because something pushes it, but because there is no orbit left to fall into. This is where the accretion disk ends, the bright, hot ring of gas and dust that surrounds many black holes. The disk extends inward to roughly this boundary and no further. Beyond it, the infalling gas accelerates toward the event horizon, heating further, radiating its last energy outward before crossing the threshold from which nothing returns. The innermost stable circular orbit is, in a sense, the last place where matter can pause. The last stable address before the long fall inward. And it is worth sitting with that for a moment. 3 times the Schwarzschild radius. For a black hole of 10 solar masses, that is roughly 90 kilometers from the center. A distance a fast aircraft could cross in a few minutes. And yet, within that distance, the ordinary rules of orbital mechanics no longer apply. Gravity has become so dominant, space-time so curved, that the familiar balance between inward pull and outward momentum simply dissolves. What lies beyond that boundary is not empty space in any ordinary sense. It is a region where the geometry of the universe has been bent so severely that all paths, all possible futures for any piece of matter lead in one direction, inward. And that direction is where we are headed next. So matter crosses that boundary. And once it does, there is no orbit waiting for it on the other side. No stable path, no equilibrium, no way to circle and hold. The innermost stable circular orbit is not just a limit in the way a speed limit is a limit, something you could technically exceed if you chose to. It is a limit written into the geometry of space-time itself. Cross it, and the mathematics of orbits simply stops working. The solutions that describe a stable circular path cease to exist. What remains is a single direction and a single outcome. In falling matter spirals inward, inevitably. There is something almost restful in that word. Inevitable. Not violent, not chaotic, just the quiet logic of a universe following its own rules to their conclusion. The matter does not struggle. It follows the only path available to it. And that path leads inward, always inward, toward the event horizon and whatever lies beyond. But before we cross that threshold, it is worth pausing here, because not all black holes are alike, and the differences between them shape everything about what the space around them looks like. The black holes we have been describing so far, the ones with a clean, spherical event horizon and a Schwarzschild radius, are idealized. They are non-rotating, and in nature, that is almost certainly rare. Stars rotate. When they collapse, that rotation is preserved, often amplified. Most black holes we expect to find in the universe are spinning, some of them very rapidly indeed. A spinning black hole is described not by the Schwarzschild solution, but by a different set of equations, worked out by the mathematician Roy Kerr in 1963. The Kerr solution is more complex, and the geometry it describes is stranger. Because a rotating black hole does not just sit there, curving spacetime around it, it drags spacetime with it. Imagine the surface of a deep, still lake, and then imagine something beneath the surface beginning to spin. The water near it would be pulled along, rotating with the object, even if nothing were pushing it directly. Spacetime near a rotating black hole behaves in something like this way. The rotation of the black hole pulls the fabric of space itself into motion. Everything in the vicinity, light, matter, even the vacuum, is swept along in the direction of the spin. This is called frame dragging. And it creates a region around the black hole that has no equivalent in the non-rotating case, a region outside the event horizon, but where the effects of that rotation become inescapable. This region is called the ergosphere. Within the ergosphere, it is no longer possible to remain stationary with respect to the distant universe. No matter how powerful your engines, no matter how hard you push against the current, spacetime itself is moving, and you move with it. You can still escape. The ergosphere is outside the event horizon, and escape is still possible, but you cannot stand still. The universe, in this small region, has a direction built into it. There is something quietly profound about that. The idea that space itself can rotate, that the geometry of the universe near a spinning mass is not symmetric in all directions, but has a kind of handedness, a preferred sense of motion. It is one of the stranger predictions of general relativity, and it has been confirmed, in much weaker form, around the rotating Earth itself. The ergosphere also makes possible something remarkable, a way of extracting energy from the black hole itself. The physicist Roger Penrose described a process in which an object entering the ergosphere could, under the right conditions, split into two pieces. One piece falls inward, past the event horizon. The other escapes outward, and the escaping piece carries away more energy than the original object brought in. The extra energy comes from the rotation of the black hole. The infalling piece carries negative energy, in the precise sense defined by the geometry of the ergosphere, and the black hole slows, very slightly. As a result, the outgoing piece is faster, more energetic than what entered. Energy has been extracted from the spin of the black hole itself. This is the Penrose process. It does not violate any conservation law. It is a genuine mechanism, permitted by the mathematics, by which a rotating black hole can lose rotational energy over time. In astrophysical settings, related processes involving magnetic fields and plasma may be responsible for some of the enormous jets of energy that certain black holes launch into space. The ergosphere is not just a curiosity. It is, in a sense, a reservoir. And now, as we draw closer to the event horizon itself, something else begins to happen. Something that general relativity predicts with quiet precision, and that has been measured in weaker form right here on Earth. Time slows down. This is not a metaphor. It is not a way of saying that things seem to happen more slowly near a black hole. It is a statement about the actual rate at which time passes, the rate at which clocks tick, atoms vibrate, processes unfold, and how that rate depends on the depth of a gravitational field. Gravitational time dilation is a direct prediction of general relativity. Einstein's equations say that the deeper you are in a gravitational well, the more slowly time passes for you relative to someone higher up. This has been confirmed with atomic clocks on aircraft, with clocks at different altitudes on Earth, with the precise timing corrections required to make GPS satellites work. It is not theoretical in the sense of being unverified. It is a measured feature of the universe we live in. Near a black hole, this effect becomes extreme. A clock hovering just above the event horizon, held there by some impossibly powerful engine, fighting the pull of gravity, would tick almost infinitely slowly compared to a clock far away. An observer watching from a safe distance would see that clock running slower and slower as it descended. The ticking would stretch out, the intervals between each tick growing longer and longer, until, at the event horizon itself, the clock would appear to stop entirely. From the distant observer's perspective, time at the event horizon has frozen. This is not an illusion caused by the travel time of light, though that plays a role in the appearance. It is a genuine feature of the geometry. The event horizon is a place where, from the outside, time, as measured by a hovering clock, comes to a halt. And this creates one of the most quietly disorienting features of black hole physics. Because from the perspective of the infalling observer, the one actually crossing the horizon, nothing dramatic happens at that moment. Time does not stop for them. They do not feel themselves freeze. They cross the horizon in finite time by their own clock, and the crossing itself is, depending on the size of the black hole, entirely unremarkable in the local sense. Two observers, watching the same event, arriving at completely different descriptions of what happened. One sees an object frozen at the boundary of the universe, suspended forever at the edge of the horizon, slowly fading and reddening as its light is stretched by gravity. The other simply continues. Both descriptions are correct within their own frames of reference. Neither observer is wrong. The universe permits both experiences simultaneously, and general relativity holds them together without contradiction, though not without a deep and unresolved tension that physicists are still working to understand. This is the nature of the threshold we are approaching. Not a wall, not a surface you could touch or feel, but a boundary written in time itself, where the geometry of the universe draws a line between what can be seen and what cannot, between what can escape and what cannot, between the universe we know and something else entirely. And so we find ourselves at the threshold, not yet inside, but close enough to feel the geometry shift. Close enough to understand that what happens next depends entirely on where you are standing, or rather, where you are falling. We have already seen how two observers can watch the same event and arrive at entirely different accounts of it. The distant observer, safe and still, watching an object slow and redden and freeze at the edge of the horizon. The infalling observer, carried forward by the curvature of space-time itself, crossing that same boundary without ceremony, without drama, without any local sign that something profound has occurred. This is not a paradox in the sense of a contradiction. It is something stranger than that. It is the universe holding two truths at once, each one valid within its own frame, each one incompatible with the other if you try to force them into a single picture. Physicists have a name for the older picture, the one where the infalling object appears to freeze. They sometimes call it the frozen star. It was all for a time the dominant way of thinking about what a black hole actually was, an object so dense that time itself seemed to stop at its surface, a star that had collapsed inward and then simply paused, suspended at the edge of its own gravity. But the frozen star picture, while not wrong exactly, is incomplete. It describes only what a distant observer can ever see. It says nothing about what happens beyond that boundary. And beyond that boundary, as far as general relativity can tell us, the story continues. The infalling observer does not freeze. They do not hover at the edge of time. They cross. And once they cross, the geometry of space-time changes in a way that has no analogy in ordinary experience. Inside the event horizon, the direction toward the singularity is no longer simply a direction in space. It becomes, in a precise mathematical sense, a direction in time. Moving inward is not a choice. It is as inevitable as the passage of moments, as unavoidable as tomorrow. But we are not quite there yet. Before we reach the horizon, before we even approach it closely, there is something else to consider, something that would make itself known long before any boundary was crossed. Gravity does not pull on all parts of an extended object equally. This is a simple fact, and a quiet one, but its consequences are profound. When you stand on the surface of the Earth, the ground beneath your feet is slightly closer to the center of the planet than the top of your head. The gravitational pull on your feet is, by a tiny fraction, stronger than the pull on your head. The difference is so small that you never feel it. Your body holds together without effort, and the tidal force, as it is called, is entirely negligible. But near a black hole, that difference is not negligible. Tidal forces scale with the gradient of gravity, how quickly the gravitational pull changes over a given distance. And near a stellar mass black hole, that gradient becomes extreme. The difference in gravitational pull between one end of an object and the other can become enormous, even over very short distances. For a human body falling toward a stellar mass black hole, one perhaps 10 times the mass of the Sun, the tidal forces would become lethal long before the event horizon was ever reached. The pull on the feet, if falling feet first, would be so much stronger than the pull on the head that the body would be stretched, gently at first, then with increasing force, drawn out along the direction of fall into something longer and thinner than any human form was meant to be. This process has a name that is informal but precise in its imagery: spaghettification. The gradual, then rapid, stretching of matter into a thin strand by the differential pull of gravity. It is not a violent tearing, at least not initially. It is more like a slow elongation, a drawing out. The way a piece of warm glass can be pulled into a thread if the force is applied steadily and the material has no choice but to yield. For a stellar mass black hole, this would happen well outside the event horizon. The geometry of space-time near such an object is so tightly curved, the gradient so steep, that the tidal forces reach lethal intensity at a considerable distance from the boundary itself. The event horizon, in this case, would never be reached intact. And yet, for a supermassive black hole, one containing billions of solar masses, like the one at the center of galaxy M87, the situation is different in a way that is quietly remarkable. The event horizon of such a black hole is vast. Its Schwarzschild radius stretches across a region larger than our entire solar system. And because the horizon is so large, the gradient of gravity at that boundary, the rate at which the gravitational pull changes from one side of an object to the other, is actually quite gentle. Tidal forces at the event horizon of a supermassive black hole can be no stronger than the tidal forces you might feel from the moon. Mild, imperceptible to any ordinary sense. An extended object, a spacecraft, a body, a cloud of gas, could cross the event horizon of such a black hole entirely intact, with no local sign that anything unusual had occurred. This is one of the quieter wonders of black hole physics, that the most extreme objects in the universe are not all extreme in the same way, that a smaller black hole, in some respects, is more immediately violent than a larger one, that the boundary of no return for a sufficiently massive black hole could be crossed in a moment of perfect calm. The infalling observer would feel nothing. The geometry would shift around them without announcement. The horizon would pass, and they would not know it had passed. They would look around and see the same stars, the same light, the same universe they had always known for a little while longer. What they would not know, and could not know, is that the geometry of space-time had already closed behind them, that the path back to the outside universe had already ceased to exist. Not blocked, not locked, simply gone. The way a moment in time is gone once it is passed, irretrievably, without drama, without a door closing or a light going out. This is the nature of the event horizon for the infalling observer. Not a wall, not a surface, not a place where anything feels different, but a point of no return written into the structure of space-time itself, invisible from the inside, definitive from the outside. Two observers, the same event, two entirely different experiences, and no way, even in principle, to reconcile them into a single shared account. The universe does not offer a view from nowhere. Every description of what happens near a black hole depends on who is describing it, and from where, and whether they are falling or hovering or watching from a safe and distant place. And this quiet, unresolvable difference in perspective is not a flaw in our understanding. It is one of the deepest things general relativity has told us about the nature of reality. That space and time are not a fixed stage on which events occur. They are themselves part of the story, shaped by mass, curved by gravity, experienced differently by every observer moving through them. The black hole does not sit inside the universe the way an object sits inside a room. It is a place where the universe itself has folded inward, where the geometry of space-time has drawn a boundary that no light, no signal, no information can cross from the inside out. And somewhere beyond that boundary, the story continues. But before the horizon, before the crossing, there is something else worth resting with for a moment. The way matter behaves as it approaches. Not all matter falls cleanly inward. Not all of it arrives at the event horizon in one quiet piece. For anything extended, anything with length, with structure, with parts that are closer and parts that are farther, the black hole does not pull evenly. Gravity falls off with distance, and near a black hole, that fall is steep. The near side of an object feels a stronger pull than the far side, and that difference, that gradient, is what we call a tidal force. The same principle that raises the oceans on opposite sides of the Earth, stretched to an extreme that the Earth could never produce. Near a stellar mass black hole, those tidal forces become overwhelming well before the event horizon is reached. An extended object, anything with appreciable size, would be pulled along its length and compressed from the sides, drawn out into something long and thin, the way soft material stretches when pulled from both ends. Physicists have a name for this, an informal one, but an accurate one. Spaghettification. It is not a dramatic word for a dramatic idea. It is simply a description of what the geometry does to matter that cannot hold itself together against a gradient that's steep. The object does not explode. It elongates, quietly, inevitably, in the direction of the pull, until it is no longer recognizable as what it was. Near a supermassive black hole, as we touched on earlier, the tidal forces at the horizon can be gentle enough that large objects cross intact. But for stellar mass black holes, the stretching begins far outside, long before any boundary is reached. And so matter arrives at a black hole in many different states. Some of it falls in directly, some of it is torn apart on the way, and some of it never falls in at all. At least, not right away. When gas or dust or the remnants of a disrupted star approach a black hole with any sideways motion, any angular momentum, it cannot simply drop straight inward. The same principle that keeps planets in orbit around the Sun applies here. A moving object with sideways velocity will tend to curve around rather than fall through. And so the infalling material begins to orbit. But orbits at different distances move at different speeds. The inner material moves faster than the outer material, and where layers of gas at different speeds rub against each other, there is friction. And where there is friction, there is heat. This is how an accretion disk forms. Not by design, not by any organizing force, but simply because angular momentum and friction and gravity, left to themselves, naturally produce a flattened, rotating structure, a disk of gas spiraling slowly inward, layer by layer, as friction bleeds away its angular momentum and lets it sink. The disk is not quiet. The friction that drives the inward spiral also heats the gas, and near a black hole, the heating is extreme. The inner regions of an accretion disk can reach temperatures of millions of degrees, not thousands, not tens of thousands, millions. At those temperatures, matter does not simply glow with visible light. It radiates across the full electromagnetic spectrum, infrared, ultraviolet, and deep into the X-ray band. The innermost edge of the disk, where the gas is hottest and moving fastest, glows in X-rays. This is, in fact, one of the primary ways we detect black holes that would otherwise be invisible. We look for the X-ray glow of their accretion disks. We look for the signature of gas heated to temperatures that nothing else in the ordinary universe can produce. The disk itself is not uniform in brightness. There is a subtlety here that general relativity introduces. When a source of light is moving toward you, its light is compressed, shifted toward the blue end of the spectrum, and made brighter. When it moves away, the light is stretched, dimmed, shifted toward the red. This is the Doppler effect, familiar from sound. But at the speeds involved near a black hole, the effect becomes relativistic, and the brightening on the approaching side is significant. One side of the accretion disk is moving toward the observer, the other side is moving away, and so the disk appears asymmetric. One arc of the ring is noticeably brighter than the other, not because the gas there is hotter or denser, but because of the direction of its motion relative to the line of sight. This effect, relativistic beaming, is visible in the first image ever captured of a black hole's shadow. The bright ring around the dark center is not uniformly bright. It is brighter on one side, and that asymmetry is not an artifact. It is the geometry of motion written in light. There is something quietly remarkable about that an image of a black hole, taken from a distance of 55 million light years, carries within it the signature of gas moving at a significant fraction of the speed of light, that the physics is legible even across that distance. And then there are the jets. Some black holes, not all, but some, do something that accretion disks alone cannot explain. They launch narrow streams of plasma outward, perpendicular to the disk, not inward, not sideways, but straight out along the rotation axis, in both directions at once. These jets can extend for thousands of light years. In some cases, tens of thousands. In the most extreme cases, hundreds of thousands. Structures that dwarf the galaxy they emerge from, launched from a region smaller than our solar system, sustained over timescales that are difficult to hold in the mind. The mechanism that produces them is still not fully understood. Magnetic fields are almost certainly involved. The rotating plasma of the accretion disk generates and amplifies magnetic fields, and those fields can act as channels, collimating and accelerating material along the rotation axis. The Blanford-Zinayak process, a theoretical mechanism involving the spin of the black hole itself, is one of the leading candidates. But the details of how jets are launched, how they remain collimated over such vast distances, how they carry so much energy without dispersing. These remain active questions. What is clear is that the jet is not simply matter escaping. The black hole is not leaking. The jet originates outside the event horizon, from the disk in the region just above it. It is energy extracted from the system, from the rotation, from the magnetic fields, from the infalling material, and redirected outward with extraordinary efficiency. A black hole, in this sense, is not only a destination, it is also a source. The same object that draws matter inward, that bends light, that curves space-time into a one-way boundary. That same object can power structures that extend across a significant fraction of a galaxy, can heat the surrounding gas, can shape the environment for millions of light years in every direction. The black hole does not simply consume, it transforms. Matter falls in. Energy comes out, not from inside the horizon, but from the turbulent, heated, magnetically threaded region just outside it, from the disk, from the jets, from the slow inward spiral of gas that has been circling for thousands of years before it finally crosses the last stable orbit and begins its final descent. And all of this, the disk, the jets, the X-ray glow, the asymmetric brightness, all of it is happening right now, in the centers of galaxies scattered across the observable universe, quietly, at distances so vast that the light reaching us left before the Earth existed. The universe is full of this, and most of it we will never see directly. What powers those jets? What shapes them? What keeps them narrow across thousands of light years is something physics has not yet fully answered. The leading picture involves magnetic fields, fields that thread through the accretion disk, that wind and twist as the disk rotates, that may reach down into the ergosphere of a spinning black hole and tap the rotational energy of space-time itself. The plasma is funneled, accelerated, collimated, sent outward in two narrow beams moving at a significant fraction of the speed of light. But the precise mechanism, the exact sequence of events that takes infalling gas and redirects it into something so ordered, so directional, that remains an open question. It is one of the more humbling aspects of black hole physics that we can image the shadow of a black hole 6.5 billion times the mass of the Sun, that we can detect the ripple of two merging black holes from a billion light years away. And yet the question of how a jet stays narrow across a distance larger than most galaxies, that question is still being worked out. Science holds many things at once: certainty in some places, genuine uncertainty in others. And the honest answer here is that we are still learning. And so the jets extend outward, and the disk continues to glow. And occasionally, something else happens. A star wanders too close. Stars in the centers of galaxies move on long, slow orbits, but those orbits are not always stable. A gravitational nudge from a passing object, a slow drift over millions of years, and a star that once circled safely at a comfortable distance can find itself on a new path, one that brings it closer and closer to the supermassive black hole at the galaxy's heart. When it gets close enough, the tidal forces take over. The same principle that would stretch a human body near a stellar mass black hole applies here, at a much larger scale. The near side of the star feels a stronger gravitational pull than the far side, and if the difference is large enough, the star cannot hold itself together. Its own gravity, the force that has kept it intact for millions or billions of years, is simply overwhelmed. The star is disrupted, pulled apart, stretched into a long, curving stream of gas that wraps around the black hole. This is called a tidal disruption event. Some of that gas escapes entirely. Some of it falls inward, joining the accretion flow, heating up, radiating. And for a brief period, weeks, sometimes months, the flare of light produced by this infalling debris can outshine the entire host galaxy. Every star in that galaxy, every 100 billion suns quietly burning, temporarily dimmed, in terms of total output by the death of a single star falling into a single black hole. These events are visible across enormous distances. They appear as sudden brightening in the centers of otherwise quiet galaxies, galaxies with no active nucleus, no ongoing accretion, no jets, just a dormant black hole that has, for a moment, been fed. Astronomers now detect them regularly, each one a record of a star that no longer exists, each one a brief window into the feeding behavior of a black hole that had been silent for perhaps millions of years. The universe is patient. It waits. And then, when the geometry is right, it acts. And sometimes, the geometry involves not one black hole, but two. Black holes can orbit each other. Two stellar mass black holes, each the remnant of a massive star, can find themselves bound together in a binary system, circling one another across years, decades, centuries, slowly losing energy to gravitational radiation, drawing closer. The in-spiral is gradual at first, almost imperceptible, but as the two objects approach, the rate of energy loss increases. The orbit tightens. The objects move faster and faster until they merge. In September of 2015, detectors on Earth registered a signal that had traveled roughly 1.5 billion light-years to reach them, a faint stretching and compressing of space-time, lasting less than a second, produced by two black holes, one about 36 times the mass of the Sun, the other about 29, completing their final orbit and becoming one. The signal was called GW150914. It was the first direct detection of gravitational waves, and what it represented was almost difficult to hold in the mind quietly. In the final fraction of a second before merger, those two black holes were radiating more power and gravitational waves than all the stars in the observable universe combined were radiating in light. For that brief moment, the merger outpaced the entire visible cosmos in terms of energy output. And yet the effect on Earth was almost nothing. The wave that arrived here, after traveling 1.5 billion light-years, after passing through galaxies and voids and the slow expansion of space itself, stretched and compressed the distance between two mirrors by a fraction of the width of a proton. Less than a proton. The detectors that registered this were among the most precise measuring instruments ever built, and even they were operating at the very edge of what is physically possible to measure. 3 solar masses of energy, the equivalent of 3 entire suns, converted completely into gravitational radiation, passed through the Earth, and left behind a distortion smaller than any particle we can directly observe. This is what gravitational waves are, not a force in the ordinary sense, not a pressure or a push, but a ripple in the geometry of space and time itself, a change in the shape of the fabric that everything else moves through. Einstein predicted them in 1916, the same year Schwarzschild derived his solution from the trenches of the Eastern Front. It took nearly a century to confirm they were real, and now, detectors around the world register them with increasing regularity, each signal a record of a merger that happened long before the Earth existed, each one a message written in the language of space-time, arriving quietly, asking only for instruments sensitive enough to listen. There is something worth sitting with in that. The universe has been sending these signals for billions of years. They have been passing through every object, every body, every planet and star and empty stretch of space, undetected, unnoticed. carrying their information in a form that required both the mathematics of general relativity and a century of engineering to finally receive. We were always inside the signal. We just didn't know how to hear it. And this is, in some ways, the recurring theme of black hole physics. Not destruction, not drama, but information. The question of what is carried, what is preserved, what is lost. The question of whether the universe keeps records, and if so, where. A black hole merger sends its record outward in gravitational waves. A tidal disruption event sends its record outward in light. A jet carries energy across a galaxy and leaves its mark on the gas it touches. Everything that happens near a black hole leaves some trace in the surrounding universe. Everything, perhaps, except what crosses the horizon. And that is where the story becomes something quieter and stranger and harder to resolve. And that is where Stephen Hawking arrived. In 1974, he was not studying destruction. He was not studying what falls in. He was studying the boundary itself, the event horizon, and what quantum mechanics has to say about the space just outside it. What he found was unexpected. A black hole, according to general relativity alone, is perfectly cold. It absorbs everything and emits nothing. It has no temperature in the classical sense, because temperature requires radiation, and nothing can escape. But quantum mechanics does not allow a region of space to be perfectly empty. Even in a vacuum, even in the stillest, most featureless stretch of space imaginable, quantum fields are never truly at rest. They fluctuate. They ripple. Pairs of particles briefly flicker into existence and annihilate each other almost instantly, borrowing energy from the vacuum and returning it before any lasting change is made. This is not a metaphor. It is a measurable feature of quantum field theory. Near the event horizon, something different happens. When one of these fleeting pairs appears just outside the horizon, there is a small but real probability that one member of the pair falls inward while the other escapes outward. The pair cannot annihilate. The one that escapes carries energy away from the black hole, and the one that falls in carries, in effect, negative energy, reducing the black hole's total mass by a tiny, almost immeasurably small amount. The black hole has radiated. Not because anything escaped from inside it. Nothing crosses the horizon outward. The radiation originates outside, in the quantum behavior of fields in curved spacetime. The event horizon is the cause, not the source. Hawking showed that this radiation has a precise thermal spectrum, the same kind of smooth, continuous glow that a warm object emits. A black hole, quantum mechanics insists, has a temperature, and that temperature depends on mass. The relationship is inverse. The more massive the black hole, the lower its temperature. The less massive, the higher. A black hole with the mass of the sun would have a Hawking temperature of roughly 60 nanokelvins, 60 billionths of a degree above absolute zero. That is not merely cold. It is cold in a way that is almost impossible to hold in the mind. The coldest natural environments we know of in the universe are still warmer than that. And the universe itself, even now, is not that cold. The cosmic microwave background, the faint thermal glow left over from the early universe, filling all of space in every direction, has a temperature of about 2.7 kelvins. That is still roughly 45 million times warmer than the Hawking temperature of a solar mass black hole. This matters because a black hole does not simply radiate into nothing. It radiates into the universe. And if the universe around it is warmer than the black hole itself, the black hole absorbs more radiation than it emits. It gains energy. It grows, or at least does not shrink. A stellar mass black hole, sitting in the universe as it exists today, is not evaporating. It cannot be. The ambient temperature of the cosmos is too high. The black hole is, in thermal terms, colder than its surroundings, and heat flows from warm to cold, not the other way. For a black hole to begin losing mass to Hawking radiation, the universe would first have to cool below the black hole's own temperature. And the universe is cooling very slowly. As it expands, the cosmic microwave background stretches and cools. Given enough time, an almost incomprehensible amount of time, the background temperature will fall below even the Hawking temperature of a stellar mass black hole. Only then does the balance tip. Only then does the black hole begin, in the most gradual way imaginable, to lose more than it gains. The timescale for this process is not something human language handles gracefully. For a stellar mass black hole, the evaporation time, from the moment it begins losing mass to the moment it is gone, is on the order of 10 to the power of 67 years. 10 to the 67? The current age of the universe is roughly 14 billion years, written as a power of 10. That is about 10 to the 10. The evaporation timescale is 10 to the 67. The difference between those two exponents, 57 orders of magnitude, is itself a number that dwarfs the age of the universe many times over. There is no useful analogy for this. Any comparison collapses under the weight of the number. It is simply a duration so vast that the universe as we know it, its stars, its galaxies, its current structure, will be unrecognizable long before a stellar mass black hole has lost any meaningful fraction of its mass to Hawking radiation. The stars will have burned out. The galaxies will have dispersed or merged into dark remnants. The protons themselves may have decayed, if certain extensions of particle physics are correct, and still the black holes will remain, cooling imperceptibly, radiating at temperatures so low that no instrument we can conceive of today could detect them. They will be the last bright things, though bright is not the right word. They will be the last things, radiating in wavelengths so long and so faint that the universe around them will be, for all practical purposes, dark and still. And then, at the very end of that unimaginable duration, something changes. As a black hole loses mass, its temperature rises. The relationship is inverse, and it holds all the way down. A smaller black hole is hotter. As it shrinks, it radiates more intensely, which causes it to shrink faster, which raises its temperature further. The process accelerates. In the final moments, and moments is perhaps too generous a word for what may be a very brief interval, the black hole's temperature climbs steeply. Its remaining mass converts to energy in a last burst of radiation, and then it is gone. What remains is an open question. Some calculations suggest a small remnant. Others suggest complete evaporation, leaving nothing but the radiation itself spreading outward through an ancient and nearly empty universe. Either way, the information question returns here, quietly, at the end. All the matter that ever fell into that black hole, the gas, the stars, the light, the gravitational waves, the debris of tidal disruption events, all of it contributed to the black hole's mass. And as the black hole evaporates, that mass is returned to the universe as thermal radiation. But thermal radiation, in its simplest form, carries no specific information about what produced it. It is characterized only by temperature. It does not, on its surface, remember whether the information is truly lost, or whether it is encoded in subtle correlations within the outgoing radiation that we do not yet know how to read. This is the information paradox. and it remains one of the deepest unresolved questions in theoretical physics. Hawking radiation is, in a sense, the universe's way of insisting that black holes are not eternal. They are long-lived beyond any scale that has meaning to us, but they are not permanent. They participate in the universe's slow accounting. They hold what falls into them for durations that exceed the current age of the cosmos by factors that language cannot carry, and then, eventually, they give it back. In what form, and with what fidelity, we do not yet know. And yet, even knowing that, even holding the vast timescale of evaporation in mind, there is something worth pausing on at the very end, because the end is not quiet. As a black hole loses mass, its temperature rises, slowly at first, imperceptibly, over durations that dwarf the current age of the universe. But as the mass diminishes, the temperature climbs. And as the temperature climbs, the radiation intensifies. And in the final moments, the last fractions of a second of a process that took longer than anything we have words for, the black hole releases its remaining energy in a brief, intense burst. A flash at the end of an almost infinite patience. What that burst contains, and what it means, is something physics is still working toward. This is where the information paradox becomes not just a technical puzzle, but something closer to a philosophical wound in the body of physics. The question is deceptively simple to state. When matter falls into a black hole, it carries information, the precise arrangement of its atoms, the quantum states of its particles, the specific configuration that made it what it was, rather than something else. In quantum mechanics, that information is never destroyed. It may be scrambled, redistributed, made practically unreadable. But the laws of quantum mechanics insist that it is always, in principle, recoverable. A black hole seems to challenge that. When Hawking worked through the mathematics in 1974, his calculations suggested that the radiation a black hole emits is purely thermal, random, characterized only by temperature, the way the glow of a heated iron is characterized only by temperature, without memory of the ore it came from, or the hands that shaped it, or the fire that warmed it. If that were strictly true, then as the black hole evaporated, the information that had fallen in would simply cease to exist, not hidden, not encoded somewhere inaccessible, gone. And that would be a serious problem. Quantum mechanics rests on a principle called unitarity, the idea that the evolution of a quantum system is always, in principle, reversible, that information is conserved the way energy is conserved, that the universe does not forget. Hawking's result, taken at face value, said the universe does forget, that a black hole is a one-way door, not just for matter, but for the information that matter carries. For decades, this sat unresolved. Hawking himself believed information was lost. Others were not so certain. The tension between general relativity, which produced the black hole, and quantum mechanics, which forbade the loss, pointed to something deeper, a place where the two great frameworks of modern physics were genuinely, uncomfortably incompatible. Most physicists today believe information is preserved. Not because the mechanism is understood, it is not, but because the alternative, true, irreversible information loss, would require rewriting quantum mechanics in ways that create cascading problems throughout the rest of physics. The consensus has shifted, quietly but substantially, toward preservation. The question is how. One of the most striking proposals is the holographic principle. It suggests that all the information contained within a volume of space, including the interior of a black hole, can be fully encoded on the two-dimensional surface that bounds it, not as a metaphor, not as an approximation, as a precise, complete description. The event horizon, in this view, is not merely a boundary. It is a kind of surface on which the entire story of what fell is written, in some language we do not yet fully speak. This idea emerged partly from work by Jacob Bekenstein in the early 1970s and was deepened by Hawking shortly after. Together, they arrived at a formula relating a black hole's entropy to the area of its event horizon. Entropy, in thermodynamics, is a measure of the number of possible internal configurations of a system, a measure, in a sense, of hidden information. For most objects, entropy scales with volume. More space, more possible arrangements, more entropy. But for a black hole, the formula says something different. The entropy scales with the area of the event horizon, not the volume enclosed, the surface. This is the Bekenstein-Hawking formula, and it is one of the most quietly remarkable results in theoretical physics. It means that as a black hole grows, its information capacity grows with the area of its horizon, which increases more slowly than the volume would. It means that the interior of a black hole, however vast it may be in some geometric sense, is in some deeper sense described entirely by its boundary. There is something almost meditative in that. The idea that depth is an illusion, that what lies within is fully captured by what surrounds it, that the surface holds the story. This was one of the first places where gravity and quantum mechanics seemed to be speaking the same language, however haltingly. The entropy of a black hole, derived from the geometry of curved spacetime, matched the kind of entropy that quantum mechanics assigns to systems with hidden internal states. The numbers agreed, the structures rhymed. It did not resolve the information paradox, but it suggested that the resolution, when it comes, will involve a deep connection between the geometry of space and the quantum nature of information, a connection we are only beginning to trace. The holographic principle has since grown into a broader framework. In certain theoretical settings, a full quantum theory of gravity in a volume of space can be shown to be mathematically equivalent to a quantum theory without gravity on the boundary of that space. The interior and the surface are, in a precise technical sense, the same theory written in different languages. What this means for the physical universe we inhabit, whether our own spacetime has this property, whether the event horizons of real black holes truly encode what falls through them, remains an open question. But the direction it points is striking. It suggests that the universe may be, at some fundamental level, a system in which information is never truly interior, never truly buried, never truly lost. That even the deepest interior of a black hole, even the region beyond the event horizon, beyond the photon sphere, beyond the innermost stable orbit, all the way to the singularity where general relativity breaks down, even there, the information is held, somehow, at the surface, waiting, perhaps, to be returned. In what form and through what mechanisms, and whether the final burst of evaporation carries it out in subtle correlations that a sufficiently complete theory could in principle decode. These are questions that sit at the frontier of physics, where the answers have not yet arrived. What has arrived is the shape of the question. A black hole is a place where mass becomes geometry, where time bends until it points inward, where the boundary between inside and outside is not a wall, but a horizon, a surface defined not by matter, but by the structure of space-time itself. And on that surface, if the holographic principle is right, is written everything that ever fell through. Every atom of every star that collapsed, every photon that crossed the threshold, every quantum state of every particle that passed beyond the point of no return. All of it encoded in the area of a boundary, in the geometry of a horizon, in the quiet mathematics of a surface that, to a passing observer, would look like nothing at all. The universe keeps its records in unexpected places. And black holes, for all their reputation as destroyers, as endings, as the places where physics runs out of words, may turn out to be, in some sense, the most faithful archivists of all. That relationship between area and entropy, between the geometry of a horizon and the information it holds, was not just a curiosity. It was a signal, a quiet suggestion, arriving decades before anyone knew quite what to do with it, that gravity and quantum mechanics are not two separate languages describing two separate worlds. They are, somehow, the same conversation. The Wittgenstein-Hawking formula did not prove that. It did not hand physicists a unified theory, but it pointed the way a shadow points toward a source of light, towards something deeper, something that a complete description of nature would eventually have to account for. And that pointing matters, because the two great pillars of modern physics, general relativity, which describes the large, the curved, the gravitational, and quantum mechanics, which describes the small, the probabilistic, the discrete, do not, as yet, fit together into a single coherent framework. They each work, within their own domain, with extraordinary precision. But at the extremes, at the places where both must apply simultaneously, they fall silent. Or worse, they contradict. A black hole is one of those places. Consider what happens inside the event horizon. From the outside, the horizon looks like a boundary in space, a sphere, a surface you could, in principle, point toward. But once you cross it, something changes in the geometry of space-time itself. The radial direction, the direction pointing inward, toward the center, ceases to be a direction in space. It becomes a direction in time. Moving inward, past the horizon, is no longer a choice about where to go. It is as inevitable as the passage of time itself. You cannot stop moving toward the singularity any more than you can stop moving into the future. The geometry has rearranged itself. What was once a spatial dimension has become temporal, and time, inside a black hole, flows only one way, inward. This is not a metaphor. It is a direct consequence of the mathematics, of the way the Schwarzschild solution describes space-time inside the horizon. The coordinates that once described distance now describe duration. The future, for anything that has crossed the threshold, points toward the center. And nothing, no signal, no particle, no information of any kind, can travel back. Once inside, the outside universe is not merely distant. It is in the past. There is something worth sitting with in that. The event horizon is not a wall. It exerts no force. An infalling observer, crossing it, feels nothing locally dramatic, particularly near a supermassive black hole, where tidal forces at the horizon can be gentle. And yet the crossing is absolute. The moment of passage is, in a deep sense, irreversible, not because something blocks the way back, but because the way back no longer exists in the structure of space-time. The outside universe has not disappeared. It is still there, still unfolding. But it is now causally unreachable, separated not by distance, but by the geometry of what time means inside that boundary. All of this, the frozen appearance from outside, the smooth crossing from within, the inward-pointing future, follows from general relativity alone. And general relativity, followed inward, leads somewhere it cannot fully describe. At the center of a non-rotating black hole, the mathematics arrives at a singularity, a point where the curvature of space-time does not merely become large, it becomes infinite. Density without limit, curvature without bound. A place where the equations that have described everything else, the orbits, the lensing, the time dilation, the accretion, simply cease to produce finite answers. The singularity is, in the language of mathematics, a breakdown, and physicists are careful about what that means. It does not necessarily mean that something infinitely dense actually exists at the center of every black hole. It means, more precisely, that general relativity has reached the edge of its own validity. The theory is telling us, in the only way a theory can, that it no longer applies, that something else is needed. This is not a failure of general relativity in any ordinary sense. The theory has passed every experimental test it has ever been given. It predicted the bending of light around the sun, confirmed in 1919. It predicted gravitational time dilation, measured in atomic clocks aboard aircraft and satellites. It predicted gravitational waves, detected a century after Einstein wrote down the equations. It is one of the most precisely verified theories in the history of science. But it is a classical theory. It does not speak the language of quantum mechanics. It does not account for the discrete, probabilistic, fundamentally uncertain nature of reality at the smallest scales. And at the center of a black hole, those scales become relevant. The density is so extreme, the curvature so sharp, that quantum effects cannot be ignored. General relativity, applied there, is like using a map that was drawn for a different territory. Accurate everywhere it was designed to describe, and silent where it was not. A complete theory of quantum gravity, one that unifies the geometry of space-time with the principles of quantum mechanics, is expected to replace the singularity with something finite, something physically meaningful. Not an infinite point, but a region. Not a breakdown, but a description. What that description looks like, no one yet knows with certainty. Loop quantum gravity, one approach, suggests that space-time itself is not continuous but granular, woven from discrete units at the Planck scale, roughly 10 to the power of negative 35 meters. In that framework, the singularity dissolves. The curvature reaches a maximum, and then, perhaps, a bounce. String theory, another approach, embeds gravity within a broader framework of quantum fields and extra dimensions. It too suggests a singularity is an artifact, a place where the effective description breaks down, not where reality itself does. These are not competing answers so much as competing languages, each attempting to describe something that has not yet been directly observed and may never be from the outside. The interior of a black hole is, by definition, causally sealed. Whatever replaces the singularity, whatever quantum gravity describes at the center, cannot send a signal outward to confirm itself. The resolution, if it exists, is hidden. And so the black hole holds its deepest secret behind the very boundary that defines it. The event horizon is the edge of what can be known from outside. Beyond it, space-time curves inward. Time points toward the center. The singularity waits, or rather, what the singularity represents, waits, as a question that general relativity poses and cannot answer. A question that has been sitting at the heart of theoretical physics for over a century. Quietly, patiently, the way deep questions tend to wait. There is something almost restful in that. Not every question demands an immediate answer. Not every boundary demands to be crossed. Some of the most important work in physics has been the careful mapping of where understanding ends, the honest acknowledgement that here, the theory runs out and something new must begin. The singularity is one of those places, a marker at the edge of the known, not a destination, but a direction, pointing toward a theory that does not yet exist in its final form, but whose shape is slowly becoming visible in the area-entropy relationship, in the holographic principle, in the quiet mathematics of horizons and information, and the geometry of what it means to be inside. The universe is patient with its deepest answers. And tonight, so are you? Two frameworks have been proposed to carry physics beyond the singularity. Each one approaches the problem from a different direction, and each one remains, for now, unconfirmed. Loop quantum gravity treats space-time itself as something granular, not a smooth continuum, but a fabric woven from discrete loops, each one carrying a tiny quantum of area or volume. On the scales we move through every day, this granularity is invisible, but compressed matter far enough, and the discrete nature of space-time would push back. In loop quantum gravity, the singularity does not form. Instead, the collapse reaches a minimum volume and rebounds, a quantum bounce, where the inward fall becomes an outward expansion. What lies at the center of a black hole, in this picture, may not be a point of infinite density at all, but a kind of compressed beginning, a seed of something new. String theory approaches the question differently. It proposes that the fundamental constituents of nature are not point particles but tiny, vibrating strings of energy, each one far smaller than any particle we have ever measured. In string theory, the geometry of space-time emerges from the behavior of these strings, and the singularity, the place where geometry breaks down, may simply be a region where the stringy description takes over from the geometric one. The mathematics becomes different there, not infinite. The breakdown of general relativity is not a catastrophe, but a transition. Both pictures are mathematically rich. Both have produced genuine insights, and both remain, as yet, beyond the reach of any experiment we know how to perform. The singularity keeps its secret, for now, held behind the event horizon, inaccessible to any observation from outside. Perhaps that is fitting. The universe does not always reveal its deepest structure on a human timescale. There is something quietly elegant about what a black hole becomes once it has settled, once the turbulence of formation has passed, once the gravitational waves have carried away the last asymmetries, once the accretion has quieted. What remains is described, in classical general relativity, by just three numbers: mass, charge, and spin. That is all. This is the no-hair theorem, a result that emerged from the work of several physicists in the 1960s and 1970s, and whose name reflects the idea that a black hole carries no additional structure, no distinguishing features beyond those three quantities. Two black holes with the same mass, the same charge, and the same spin are, in every measurable sense, identical. It does not matter whether one formed from the collapse of a massive star and the other from the merger of two neutron stars. It does not matter what elements were present, what temperatures were reached, what complexity existed in the matter before it fell inward. All of that is gone. To an observer outside the event horizon, the black hole remembers nothing of what made it. This is one of the most striking results in all of physics. A star that spent millions of years fusing hydrogen into helium, helium into carbon, carbon into heavier and heavier elements. A star with a particular history, a particular composition, a particular structure collapses, and what remains carries no trace of any of it. The information is not merely hidden. In classical general relativity, it is lost. This is the classical statement. Quantum mechanics, as we have seen, may tell a different story, may insist that the information is preserved somewhere, somehow encoded in the Hawking radiation or in the geometry of the horizon itself. But in the smooth, geometric language of general relativity, the black hole is bare of history. 3 numbers and nothing more. There is something almost meditative in that. The universe, in this corner of its behavior, simplifies completely. Not all black holes form from the deaths of stars. Or at least, that is one possibility that physicists have taken seriously for decades. In the very early universe, in the first fractions of a second after the beginning, matter was distributed with extraordinary density, and the conditions were turbulent in ways that are difficult to fully reconstruct. In regions where density fluctuations were large enough, gravity could have overwhelmed the outward pressure and caused collapse directly, without any star as an intermediary. The black holes that might have formed this way are called primordial black holes. They are hypothetical. No primordial black hole has been confirmed by observation, but the idea is not exotic. It follows naturally from the physics of the early universe, and the question of whether they exist is one that astronomers are actively working to answer. What makes primordial black holes particularly interesting is their possible range of masses, unlike stellar mass black holes, which are bounded below by the physics of stellar collapse. Primordial black holes could, in principle, have formed with masses far smaller, perhaps as small as an asteroid, or smaller still. And unlike stellar mass black holes, which formed billions of years after the beginning, primordial black holes would have been present from nearly the start. This raises a quiet possibility, one that connects black holes to one of the deepest unsolved problems in cosmology. Most of the matter in the universe does not emit light. It does not interact with electromagnetic radiation in any way we have been able to detect. It makes itself known only through gravity, through the way galaxies rotate, through the way light bends around galaxy clusters, through the large-scale structure of the cosmos. This is dark matter, and its nature remains unknown. Primordial black holes, if they formed in sufficient numbers and with the right distribution of masses, could account for some, or perhaps all, of the dark matter. They would be dark, by definition. They would interact with ordinary matter only through gravity. They would have been present since the earliest moments of the universe. The match is not perfect, and observations have placed constraints on how many primordial black holes of various masses could exist without having already been detected. But the possibility has not been ruled out, and the search continues. It is a remarkable thought that the invisible scaffolding holding galaxies together might be made, in part, of black holes so ancient they predate every star. And then there are the giants at the centers of galaxies. Nearly every large galaxy we have studied in detail appears to harbor a supermassive black hole at its center, not as a coincidence, not as an occasional feature, but as something close to a universal characteristic. The Milky Way has Sagittarius A Stark. The galaxy M87 has the one whose shadow was imaged in 2019. Across the observable universe, wherever we find a large galaxy, we tend to find evidence of an enormous black hole at its heart. This is not simply a matter of black holes happening to live in galaxies. The relationship appears to be deeper than that. The mass of a supermassive black hole is correlated with properties of its host galaxy, particularly with the mass of the central bulge of stars, two objects that formed by entirely different processes, on entirely different scales, have grown together in a way that suggests they shaped each other. Galaxies and their central black holes seem to co-evolve. The black hole feeds on infalling gas, and as it feeds, its accretion disk radiates. Jets of plasma extend outward. Energy and momentum are deposited into the surrounding gas. This feedback can heat the interstellar medium, slow the formation of new stars, even drive gas out of the galaxy entirely. The black hole, in this sense, does not merely sit at the center of its galaxy. It participates in the galaxy's history, regulating its growth, shaping the distribution of matter across scales far larger than the black hole itself. A single object, described by three numbers, influencing the fate of hundreds of billions of stars. The universe builds its largest structures around its deepest gravitational wells. And those wells, it turns out, are not passive. They are woven into the life of everything around them. And yet, even as the black hole shapes the galaxy around it, there is something quietly strange about how little of it we can ever directly see. When astronomers captured the first image of a black hole shadow, what they were looking at was not the event horizon itself. The shadow, that dark region at the center of the glowing ring, is roughly 2.5 times larger than the event horizon. This is worth sitting with for a moment. The boundary we cannot cross is smaller than the darkness we can observe. The shadow is defined not by the horizon, but by something called the photon capture cross-section, the region from which no photon, once it begins spiraling inward, can ever escape outward again. Light that passes close enough to the black hole is drawn into a slow, tightening spiral. It never reaches the horizon in any simple straight line. It curves and curves again, and eventually crosses inward. All of those photons, every one that spirals inward rather than bending away, contribute to the darkness of the shadow. The bright ring surrounding it is the light that came just close enough to be bent dramatically, but not close enough to be captured. Light that grazed the edge of the abyss and curved back toward us across billions of light years. That ring is, in a sense, the last light that escaped, and the darkness at its center is the record of everything that did not. There's something almost meditative about this. The most dramatic boundary in the known universe announces itself not with a sharp edge, but with a gradual deepening of shadow, a slow darkening, like the sky before a storm, or the moment just before sleep. The universe does not always mark its thresholds clearly. Sometimes the most significant boundaries are the ones you cross without knowing. And that brings us to something that has occupied physicists for decades: what it would actually be like, from the inside, to cross the event horizon. From far away, as we have already seen, an infalling observer appears to slow and freeze. Their image reddens and dims. They seem to hover at the horizon forever, from the perspective of someone watching from a safe distance. But from the perspective of the infalling observer, the crossing happens in finite time. There is no wall, no flash of light, no locally dramatic moment at the horizon itself. For a supermassive black hole, the tidal forces at the horizon can be gentle enough that the crossing is, in a physical sense, unremarkable. And yet something extraordinary is happening. At the moment of crossing the event horizon, the infalling observer would look upward, back toward the universe they are leaving, and see something that has no analogy in ordinary experience. The entire future light cone of the external universe would be compressed into a shrinking circle overhead. Not a snapshot of the universe as it is at that moment, but all the light that will ever fall through the horizon after them. Every photon that will ever cross that boundary, from now until the end of time, compressed into a single diminishing circle of light above. A finite but complete record of the outside universe. All of it arriving at once, or rather, all of it visible at once, in that one direction, in that one moment of crossing. The circle would shrink as the observer fell deeper, the universe outside receding into a smaller and smaller window, until, eventually, even that window closes. There is no word for what that would look like. Physics can describe it mathematically, but the experience itself, sits at the edge of what language was built to carry. A finite record of an infinite-seeming universe, compressed into a point of light, and then gone. And this is where the deepest questions begin. Not the questions about tidal forces, or accretion disks, or jets of plasma. Those are extraordinary. But they are, in principle, answerable with better instruments and more time. The deepest questions black holes pose are of a different kind entirely. They are questions about information. When matter falls into a black hole, it carries information, the precise arrangement of every particle, every quantum state, every detail of its structure. A book falling in carries the information of every word. A star falling in carries the information of every atom. In classical general relativity, that information is simply gone. The black hole is described by three numbers: mass, charge, and spin, and nothing else. All the complexity of everything that ever fell in is erased from the outside universe. But quantum mechanics says that information cannot be destroyed. Not truly. The laws of quantum physics are reversible in principle. The past can always, in theory, be reconstructed from the present. These two statements cannot both be true. And yet both general relativity and quantum mechanics are among the most precisely tested theories in the history of science. This is the information paradox, and it remains, as of now, unresolved. Most physicists believe that information is preserved in some form, that Hawking radiation, which slowly carries energy away from the black hole over unimaginable timescales, must also carry information encoded within it. Subtly, invisibly, in correlations between particles that would take longer than the age of the universe to decode. But the precise mechanism, how information escapes, how it is encoded, what it means for the structure of space-time near the horizon, is still an open question. Some approaches suggest that the event horizon is not the smooth, featureless boundary that general relativity describes, that quantum effects make it something more complex, a surface that scrambles and re-emits information in a form we do not yet fully understand. Others suggest that the answer lies in the holographic principle, the idea that all the information inside a black hole is encoded on its two-dimensional surface, the way a hologram encodes a three-dimensional image on a flat plate. If this is true, then the interior of a black hole is, in some deep sense, a projection, and the boundary between inside and outside is not a wall, but a kind of screen. These ideas are not yet confirmed. They are the frontier of theoretical physics, where mathematics reaches further than experiment can currently follow. And perhaps that is fitting. Black holes have always been places where our understanding reaches its limit, where the equations that describe the universe so precisely everywhere else begin to strain and then break. The singularity at the center, where curvature becomes infinite, where the equations return no meaningful answer, is not a description of what is there. It is a description of where our description fails. General relativity, which predicted black holes before anyone believed they were real, also predicts its own incompleteness at their centers. A complete theory, one that unifies gravity with quantum mechanics, would replace the singularity with something finite, something physically meaningful, something we do not yet have the mathematics to write down. And so black holes sit at the intersection of everything we know and everything we do not. They are the places where time slows and then stops, where space curves back on itself, where the future becomes a direction you can only move toward, never away from. They are the places where the universe keeps its deepest secrets, not out of indifference, but because the questions themselves are still being formed. The deepest question a black hole poses is not about destruction. It is about the nature of information and time and the limits of what any description of reality can ever contain. And that question, quiet, patient, unresolved, drifts with you now into the dark, into the stillness, into sleep. There is a silence in the universe. Not the silence of an empty room, but the silence of a vast forest where you expect birdsong and hear nothing. The cosmos is roughly 13.5 billion years old. It contains somewhere between 100 billion and 2 trillion galaxies. Each galaxy holds hundreds of billions of stars. Many of those stars have planets. Many of those planets sit within the range of temperatures where liquid water can exist. The numbers are almost too large to hold. And yet, no signal, no structure, no unmistakable sign that anyone else is out there. This is the question the astronomer Enrico Fermi is said to have raised over lunch in 1950, in a few quiet words that have never quite stopped echoing. If the universe is this old and this large, and the ingredients for life appear this common, then where is everybody? That question has no agreed answer. What it has, instead, is a set of possibilities, each one quiet in its own way, each one worth sitting with. The first possibility is that life, even simple life, is extraordinarily rare. The conditions that produced life on Earth may look common from a distance, but be vanishingly unlikely in practice. A planet needs not just liquid water, but a stable orbit, a large moon to steady its axial tilt, a giant outer planet to deflect incoming debris, a magnetic field to shield its surface, a star that burns steadily for billions of years without sterilizing flares. Each condition, taken alone, seems manageable. Together, they may form a combination so specific that Earth is, if not unique, then deeply unusual. This is sometimes called the rare Earth hypothesis. The idea that complex life requires a confluence of factors so precise that it has arisen only once, or nearly once, in the observable universe. If that is true, the silence makes sense. There is no one to call. But there is another possibility, one that sits differently in the mind. Perhaps life arises readily. Perhaps simple organisms have taken hold on countless worlds, and perhaps something stops them reliably before they ever reach the point of sending signals across the stars. This is the idea of the Great Filter. The phrase was introduced by the economist Robin Hanson in the late 1990s. It describes a barrier, or a series of barriers, so difficult to cross that almost no lineage of life ever crosses it. A filter through which the vast majority of potential civilizations never pass. The question the Great Filter raises is not whether it exists. The silence of the sky suggests something is filtering. The question is where it sits. Is it behind us or ahead? If the filter lies behind us, if the hard step was something in our past, then we may be among the rare few who made it through. The origin of life itself is a candidate. The jump from simple chemistry to self-replicating molecules is not well understood and may have required conditions so specific that it happened only rarely across cosmic history. The emergence of the eukaryotic cell, the complex cell with a nucleus, the kind that all plants and animals are built from, took roughly 2 billion years to appear on Earth after life began. That delay may not be coincidence. It may reflect how genuinely difficult that transition is. The emergence of multicellular life, of nervous systems, of language and abstract reasoning. Each step may have been a filter in itself, a narrow gate through which most lineages never passed. If all the hard steps are behind us, the silence is almost comforting. It means we are rare, but we are through. The road ahead, while uncertain is open. But if the filter lies ahead, that is a different kind of quiet. It would mean that life, and even intelligent life, arises with some regularity across the universe, that civilizations form, develop technology, reach the point of being able to communicate across interstellar distances, and then, reliably, stop. Not because of anything external, but because of something internal. A civilization that develops the capacity to reshape its world also develops the capacity to destroy it. Nuclear weapons, engineered pathogens, the slow destabilization of the systems that sustain life. These are not hypothetical concerns. They are things that exist, or could exist, within decades of a species reaching a certain level of technological capability. If nearly every civilization that reaches this threshold fails to navigate it, if self-destruction is the common fate, then the universe would look exactly as it does, full of the raw materials for intelligence, empty of its long-term products. The silence, in this reading, is not a mystery, it is a warning. And the fact that we have not yet found evidence of others may be, in a quiet and unsettling way, the most important data point we have ever encountered. There are softer possibilities too. Perhaps civilizations exist, but do not broadcast. A species that has survived long enough to become wise may also have learned caution. The act of announcing your presence across the cosmos to unknown listeners may not seem, on reflection, like a prudent thing to do. Perhaps they are listening, as we are, and waiting, as we are, and the universe is full of patient silence on all sides. Perhaps the timescales involved make contact nearly impossible, regardless of intent. A civilization that flourished and faded 2 billion years ago would leave traces so faint, so eroded by time and entropy, that we would have no way of recognizing them. The universe is old enough to have contained many stories that are simply over. Perhaps our searches have been too narrow. We have listened for radio waves, for laser pulses, for the specific signatures we ourselves might produce. But a civilization far older than ours might communicate or exist in ways we have not yet thought to look for. The observational limits are real. We have surveyed a small fraction of the stars within a modest radius of our own. The search is young, and the sky is vast. And yet the silence persists, not as proof of anything, but as a presence. There is something in the human mind that finds this silence hard to accept. We are a species that evolved in groups, that orients toward other minds, that finds meaning in connection. The idea that across all of this, all the light, all the time, all the turning worlds, we might be alone, or nearly alone, sits strangely. But strangeness is not the same as impossibility. The universe is not obligated to be populated in the way we find comfortable. It is not obligated to confirm our intuitions about what is likely. What it offers, instead, is the question itself, sitting in the dark between the stars, patient and unresolved. We are a species that has existed for a brief moment in cosmic time. We have been sending signals into space for less than a century. Our radio bubble, expanding at the speed of light, has reached only the nearest few hundred stars out of hundreds of billions. We are, in cosmic terms, very new. And perhaps that is the most honest thing to hold on to tonight. Not an answer, but a position. We are early. We are small. We are listening. The sky above you right now holds light that has traveled for millions of years to reach this world. Some of it passed through galaxies we have never named. Some of it originated before the Earth existed. And somewhere in all of that light, there may be an answer. Or there may be only the quiet. Either way, the question drifts with you now. out past the atmosphere, past the nearest stars, into the long, unhurried dark, where the universe keeps its own counsel, and you rest. There is a place in the universe where the ordinary rules quietly end. Not with violence, not with noise, but with a boundary so subtle that you could cross it without feeling a thing. And yet, on the other side, nothing. Not light, not time, not any signal ever sent can find its way back. That boundary is called the event horizon. And it is not a wall. It is not a surface you could touch or see. It is a geometric fact, a threshold written into the shape of space-time itself. Beyond a certain distance from enough compressed mass, the curvature of space becomes so severe that all paths, every possible direction anything could travel, curve inward. There is no outward anymore. A black hole begins with mass, enough mass, pressed into a small enough region that escape becomes geometrically impossible. The escape velocity, the speed something would need to leave, exceeds the speed of light. And since nothing travels faster than light, nothing leaves. The boundary where this becomes true is called the Schwarzschild radius, named for Karl Schwarzschild, who derived it in 1916 while stationed on the Eastern Front of a world war. He solved Einstein's field equations exactly in the middle of a war and sent the solution to Einstein by post. He died months later, but the mathematics remained. For an object with the mass of the Earth, the Schwarzschild radius is roughly 9 millimeters, a sphere smaller than a marble, containing everything our world is made of. For the Sun, it is about 3 kilometers. These are not the sizes of real black holes. The Earth and Sun are far too diffuse to collapse this way, but the numbers give a sense of the relationship. Mass and radius scaling together quietly. Real black holes form from stars. When a massive star exhausts its fuel, the outward pressure that held it open against gravity disappears. The core collapses. If what remains is heavy enough, the collapse does not stop. It continues past the density of neutron matter, past any known force that could resist it, and a black hole forms. Stellar mass black holes range from roughly 3 to several tens of times the mass of the Sun. And then there are the others. At the center of nearly every large galaxy, including our own, sits something far larger, a supermassive black hole. The one at the center of the Milky Way is called Sagittarius A star. Its mass is roughly 4 million times that of the Sun, contained within a region smaller than the distance from the Sun to the nearest stars. In 2019, for the first time, humanity captured an image of a black hole's shadow, not Sagittarius A star, but the supermassive black hole at the center of a galaxy called M87. Its mass is about 6.5 billion solar masses. The image showed a dark region, the shadow, surrounded by a bright, uneven ring of glowing gas. One side of the ring brighter than the other, because the gas on one side moves toward us, and light from that side is amplified by its own motion. That brightness asymmetry has a name, relativistic beaming, and it is not an artifact of the image. It is the universe behaving exactly as the equations predict. Light itself bends near a black hole. Gravity curves the paths of photons just as it curves the paths of planets. A photon passing close enough will arc around the black hole and continue on its way, carrying a distorted image of whatever lay behind. When the alignment is perfect, source, black hole, observer, the light forms a complete ring, an Einstein ring, a halo of bent starlight circling a darkness. Just outside the event horizon, there is a region where gravity is strong enough to hold photons in circular orbits. This is the photon sphere. For a non-rotating black hole, It sits at exactly 1.5 times the Schwarzschild radius. But these orbits are unstable. A photon nudged slightly inward spirals down. A photon nudged slightly outward escapes. Nothing rests there for long. Closer still, matter cannot maintain any stable orbit. The innermost stable circular orbit sits at 3 times the Schwarzschild radius. Inside that boundary, gas and dust spiral inward without the possibility of a stable path. They fall. As they fall, they heat. The accretion disk, the swirling structure of infalling gas, reaches temperatures of millions of degrees. It radiates across the entire electromagnetic spectrum. The inner edge glows in X-rays. Some black holes launch narrow jets of plasma perpendicular to the disk, extending for thousands of light years into surrounding space. The mechanism that shapes and accelerates these jets is still not fully understood. Magnetic fields are almost certainly involved, but the details remain an open question. Now consider what it would mean to fall in. To a distant observer, watching something approach the event horizon, a strange thing happens. The infalling object appears to slow. Its light redshifts toward longer and longer wavelengths. It seems to freeze, asymptotically, just above the boundary, never quite crossing, dimming and reddening until it fades from view. But from the perspective of the infalling observer, nothing dramatic happens at the horizon. The crossing occurs in finite time. There's no wall, no flash, no sensation of a threshold. The event horizon is not a place, it is a condition. A point of no return that announces itself only in retrospect. These two perspectives are both correct. They describe the same event from positions that cannot compare notes. This is not a paradox to be resolved. It is a feature of how space-time works when curvature becomes extreme. Inside the event horizon, something stranger still occurs. The radial direction, the direction pointing toward the center, becomes time-like. Moving inward is no longer a choice. It is as inevitable as moving forward through time. The singularity at the center is not a place in space that can be avoided. It is a moment in the future of everything that crosses the horizon. General relativity predicts that singularity as a point of infinite curvature. But most physicists understand this as a sign that the theory reaches its own limits there. A complete theory of quantum gravity, which does not yet exist, is expected to replace the singularity with something finite, something physically meaningful. Loop quantum gravity and string theory each offer different proposals. Neither has been confirmed. In 1974, Stephen Hawking showed that quantum effects near the event horizon cause black holes to emit a faint thermal radiation, now called Hawking radiation. The temperature of this radiation is inversely proportional to the black hole's mass. Smaller black holes are hotter. A stellar mass black hole radiates at a temperature far below the cosmic microwave background, the ambient warmth left over from the early universe, so it currently absorbs more than it emits. It will not begin to lose mass until the universe cools further. The timescale for a stellar mass black hole to evaporate completely is on the order of 10 to the power of 67 years, a number so large it has no useful comparison. And yet, in principle, it ends. In the final moments, the temperature rises. The remaining mass is released in a brief burst, and then, nothing. This raises a question that has not been answered. When matter falls into a black hole, it carries information, the specific arrangement of particles, the quantum states, the history encoded in every atom. Hawking's original calculations suggested this information was destroyed, gone, permanently, when the black hole evaporated. But destroying information would violate a foundational principle of quantum mechanics. Most physicists now believe the information survives in some form, perhaps encoded on the event horizon itself, in a way we do not yet understand. The holographic principle suggests this is possible, that the two-dimensional surface of the horizon can carry all the information of the three-dimensional interior. But the mechanism remains unresolved. A black hole is fully described in classical general relativity by just three numbers: mass, charge, spin. Everything else about the matter that formed it, its history, its composition, the lives of the stars that collapsed, is inaccessible to the outside universe. This is called the no-hair theorem, and it is one of the quieter, stranger facts in all of physics, that something so consequential can be so spare. The shadow of a black hole is larger than the event horizon itself, roughly 2.5 times larger, because the shadow includes all the photons that spiral inward rather than escape, a wider region of capture than the horizon alone defines. And at the moment of crossing that horizon, an infalling observer would look back and see the entire future of the external universe compressed into a shrinking circle of light overhead. All the light that will ever fall through the horizon, a finite but complete record of everything outside, gathered into that diminishing window. And then the window closes. What remains is the interior, the inevitable approach, the quiet that has no outside. Black holes are not, in the end, about destruction. They are about the limits of description, about what happens when the tools we use to understand the universe, space, time, information, causality, reach their own edges. We built mathematics precise enough to predict them before we had ever seen one. We bent radio telescopes across an entire planet to photograph a shadow. We detected the ripple in space-time from two of them colliding 1 billion light-years away by measuring a displacement smaller than a proton's width. And still, at the center, there is something we cannot yet describe. The question sits there, patient, in the dark. As you rest now, the atoms of your body carry their own quiet information. Every particle with its history, its state, its place in the long, unbroken chain of cause and effect stretching back to the beginning of everything. That information, as far as we can tell, is never lost. It changes form, it disperses, it becomes harder to read, but it persists. Somewhere in the mathematics of the universe, everything that has ever happened is still, in some sense, written, even this moment, even the slow settling of your breath, the dark behind your eyes, the soft weight of